So of course I'd like to thank the organizers for the invitation and for this wonderful conference. I ascertained from Ram that I first met him in 1981. Perhaps more to the point, so the first talk that I gave, invited talk that I gave outside my department was in McGill, and the invitation came from Ram. So that's certainly a confidence boosting event, and so thank you and happy birthday. So I want to, so since this is perhaps a more classical versus automorphic audience, I'll state the problem kind of in classical terms and then move to maybe Adelic language. So I want to frame a very general question, and let's see. So suppose I have a Dirichlet series. So I will give myself a Dirichlet series. Right. And of course we'll assume that it converges in some half plane. And suppose it further has an Euler product. So let me write that condition down as EP. So I'll assume that it has an Euler product of some kind. Product over P. Of course, the point of this is QP is a polynomial. And with QP of 0 equals 1, so usual kind of form. I'll assume it's, a priori I don't have to assume that the degrees are all the same, but in fact in all examples there will be, the degree of QP will be the same at almost all primes, right? QP the same. Right? I'll also assume two more conditions, and this I'll call maybe FNP, right? Namely that ds extends to a meromorphic function on C, and here is a crucial assumption with at most a finite number of poles. Poles, and perhaps the last, and then the last assumption will be ds, so maybe some function times ds satisfies so satisfies a suitable functional equation. Of course, this GS will be typically products of gamma functions, products of some factors of pi and some gamma functions. So gamma functions, right? So we've already seen many examples of these things. So of course what I have in mind is L functions associated to modular or automorphic forms, and the most special cases of course being the zeta function and those associated to Dirichlet characters. Okay, so in this context, just with this information, so let me pose the question. So can one say anything about the number and location of the poles of so let me call this function LS. The fact is, because of the functional equation and the nature of the gamma functions, ds having a finite number of poles is the same as LS having a finite number of poles, and really you can read off information both ways. Poles of LS, let's say, is for. Okay, so this is what I'm calling LS, completed L function. Okay, so this is the question. And so of course Well, the straightforward answer is no. A slightly more nuanced answer is perhaps yes, but not quite in this generality. And for instance, so let me give you one example of a yes, which is what I lectured in Montreal in 1996, is if g of s equals say gamma s and let's say b equals 1, then in fact we can even drop EP, and just this information is enough to tell us that the poles in fact occur essentially at 0 and 1, and in fact this Dirichlet series comes from a modular form on SL2 set. So it's a kind of a converse theorem but with poles. Okay, so and in that case you don't even need the Euler product assumption for just a Dirichlet series. However, there are examples. If you pass to congruent subgroups, you can in fact take any finite set and give yourself any integers, and you can in fact construct a Dirichlet series with poles exactly at those locations and exactly to those orders which satisfy the functional equation, the same functional equation as the modular form on for gamma naught n satisfies. So this tells you that the Euler product is actually crucial, and somehow that's where the arithmetic is coming in. So for the full modular group it doesn't matter, but in general EP is necessary. Okay, so this is without EP, but in general, EP is necessary. The hypothesis of EP is necessary in general. And this very general class of examples was found by Marvin Knopp way back in a paper in 1994, I think. Okay. However, so I want to attack this problem, and so anyway, let me also say what kind of answer I want, and that was indicated. So answer that I want, typically what answer would I want? Or rather, not typical so much as what I want. So what I would like. So I would like as an answer well, I'd like to know that LS has poles only at say s equals 0 and s equals 1. And of course, this will only work under suitable normalizations. So I'll say a little bit about this, but right, so this is the answer I'd really like. This is the kind of answer I'd like. Okay, so more generally you want to say that the Dirichlet series will only have poles where automorphic L functions which satisfy the same kind of equation have them or can have them. So rather, essentially the only poles that should occur should be the poles of the Eisenstein series. That's the kind of answer I would like. And of course, as I said, that's too optimistic in this complete generality. So let me, or maybe in Ram's terminology, I'd like to say that they lie in the extended Selberg class. Right? So instead of working with general Dirichlet series, I'd like to pass to cuspidal automorphic representations, or more generally, and the L functions associated to them. So the L functions themselves are not necessarily known to be the L functions of cuspidal automorphic representation. So the kind of things I have in mind are the L functions that occurred in Anandavardhan and Stock, where you take something like, you take a cuspidal automorphic pi, but then you look at things like exterior square or sim square and so on. Okay, so let's start with something, right? So pi, so cuspidal, say automorphic, and I'm going to be only on the group representation of GLN AF, and F is of course a number field. And it's known that any such pi automatically decomposes into a so-called restricted tensor product of pi v's. What are these pi v's? Pi v's are irreducible admissible representations of this time of GLN of the local field. Again, if you're seeing this for the first time, it's maybe not very helpful, but of course if you have any cuspidal eigenform, for example, on SL2, then that automatically gives rise to an object like this, a cuspidal automorphic representation. We won't have to talk too much about the representation because we'll be talking about their L functions. And okay, and in fact, almost all of these representations will be unramified, that is, they will have a vector fixed under the maximal compact subgroup of GLN FV, which happens to be GLN with entries in the ring of integers. Okay, so unramified. If I start with something cuspidal automorphic, whatever that is, almost all V. Okay, so this is my starting setup, and of course, so the question is, you know, I have certain hypotheses, EP, FNP, FE, and so on. How do I actually manufacture Dirichlet series when I know these things are true? At the very least, I need this, and so so more generally, right? So once we have pi V, there is a so-called local Langlands correspondence which attaches to this representation, rho f pi V, and what is this? Is a representation of the so-called either Way or Way-Deligne group, okay, which is like the Galois group, Way or Way-Deligne, depending on whether you're working with over the Archimedean places or. And once you have this, so this is basically like the Galois group. Once you have a representation of a Galois group, and suppose you're also given, I'm sorry, this is a complex representation, okay, and not only a complex, if I started with something on say GLR or GLN, then this will be a complex n-dimensional representation of the Way-Deligne group, and if I now have, so it will be a homomorphism into GLNC, and now if I have a representation R from GLNC, I can simply compose, okay, and I get a composite representation, and I can attach the associated Art in L function. So if I can in general, to any such irreducible thing, the local Langlands conjecture, local Langlands correspondence, what it does is to spit out an L function, right? So what is that? It's the Art in L function. By definition, LS R rho FV pi V, and the right hand side is the Art in L function. So now I have a definition. This will be the so-called local L function associated with the pi V, and if I start with a cuspidal automorphic pi, then I will simply take the product. So if I want just LS pi R, then what I do is simply take the product over all V of L, S, well, I've already defined this, so pi V R. Right, so that's okay. Now, for again, in general, it's completely unknown even how to attach L functions. Well, for GLN it's okay, but in general, for other groups, it's of course we don't even know how to attach L functions frequently. And for a still smaller class of examples, people have in fact proved that these hypotheses hold. So let me now immediately go to situation. So there are two ways in which one can get this kind of information, the three properties that I want, right? One is the following. So anyway, to start off, first of all, clearly we have an Euler product, because if I take only the V's at the finite places, that gives me an Euler product. So because the Art in L functions are exactly of that form. So what I'm really interested in is FNP and FE. Okay, so I'm not. Oh, okay. So now also let me specialize. So to a particular example, for two reasons. One is that I can't do much more right now, and the second reason is that I was also partly involved in proving properties FNP and, well, not FNP, but at least the functional equation and things like that in that case. Okay, so mostly, you know, the kind of method I'm describing ought in principle to work for, say, things like exterior square, sim square, and other such representations, but what I will take is just R equals exterior square. And so how does one get the other two properties? So for So there are two ways, so two methods of construction, right? To get, this is in general, even for other representations, to get FNP and FE, functional equation. Well, one is the so-called Langland-Shahidi method, and this was pursued by Shahidi, in this context by Shahidi and Kim Shahidi, well, Kim maybe independently also. And what that does is the following, right? So the point is, a priori you've just defined some Euler product, it's completely useless from the point of view of getting a meromorphic continuation. This Euler product will converge in some right half plane, but there's no way you know that it extends to the whole complex plane. Right? Nor will you know if there's a functional equation or not, so you need some new tools, and those tools come from harmonic analysis. Right? So the Langland-Shahidi method is one such, and indeed, but we have to be a little careful. So what people do is, they give a construction of some object. So what do? So for each pi, so for each pi v, they associated indeed something like this, and I'm going to call it LSH, SH for Shahidi. And what you can prove about these is the following, such that if well, this belongs to, well, it has the form 1 over a polynomial in QV to the minus S. This QV is of course the residue field, size the residue field of F. Okay, so they can prove this. Okay, and if V is unramified, then LSH S pi v exterior square is actually equal to L itself, which I will sometimes refer to as the Galois L function. So I'm saying that the Langland-Shahidi L function is the same as the Galois L function at all the unramified places, which is of course almost all places, all but finitely many. Okay, all right. So this they were able to do, and when pi is cuspidal automorphic, I mean, they did more, but this is what's relevant for my talk. Then they showed that FNP and FE hold for LSH S by exterior square. What's this? This is simply the product of the local Langland-Shahidi. So notice they have not actually proved, in principle they have not actually proved at this stage the theorem for the actual exterior square L function, only for their exterior square L function. So I'll come to that, which is of course the product of the local exterior square. Okay. Okay, I should be a little more careful. So in fact, in many cases, they're actually, so maybe I'll call following Piatitsky-Shapiro. If I get the answer I really want, I'll say that I'm in a nice situation, right? So in many cases they actually prove, they go beyond that and they prove that it's nice, but it's case by case. But for the most important case, which is when pi is self-dual, they're not actually able to prove anything more than this. Okay? So when pi is self-dual, there is no theorem. Notice that right now I have not yet told you that whatever L function that is even equal to the one that we started with. Okay, so that's the Langland-Shahidi, reviewed very, very quickly. So once again, just to emphasize, the question I'm asking is if this is for function fields. I don't know if there was a student of Shahidi, right? Lomer. Yeah, but did he do it for exterior square? I'm not sure. Some paper, yeah. Okay, so it's for function fields as well. For function fields, they probably get somewhat stronger statement, but I'm not sure. Okay, so that's the current status. And as I said, when pi is not self-dual, okay, when pi is not self-dual, you actually know that this L function is entire. When pi is self-dual, you would only have finiteness of poles. But anyway, the good news is, as far as this story goes, is that Henyard showed that these two are in fact the same everywhere. Well, only the ramified places were left. At the Archimedean places, it was known by earlier work of Shahidi. So I should have said perhaps if V is unramified or V divides infinity, then the theorem is true. And oh, no SH. This is true always. For all. So even at the bad places, there is the equality. So now, for the original L function, we have the three hypotheses that we need. Okay, but there's another story, which is the so-called Rankin-Selberg. So this is one way. So basically, Shahidi defined some L functions and proved that they had the relevant properties, and then between Shahidi and Henyard, they actually showed that it coincides with the original definition. Okay, so now there's the other method, is the Rankin-Selberg, which was pursued mainly by Jacques Shalaika. Okay. Sorry. And here, what do we know? Well, here the story was a little more murky. Okay, so first, once again, they have their own definition, but how does this go? So now, I'm going to assume that pi v is what's called generic. Okay, and what that means in practice is that pi v has a nice model as a function space, and it essentially sits in the class of functions w going, say, from G, L, N, F, V. So it's basically in the induced representation to C such that W of Ng transforms like a character. What's N? N is in the unipotent group. So slide aside, N is in the unipotent group, and then if we upper unipotent matrices, and psi, which is an additive character of the field, can extend naturally to the unipotent group. Okay, so I won't go into that. But the point is, you have a nice function space model. On this space of functions, G acts by right translation, and on the left, it transforms according to a character. So this is called the Whittaker model, and using this model, one is able to define an L function. So they write down an enormous integral. I'm going, just for the sake of completeness, I'm going to write it down. But okay, so what you do is you define a family of integrals, J, S, W, phi. Phi is a Schwartz function. W is in your model. You have dx, you have det, you have phi E and G. This is the usual vector in FB to the nth vector, and then you write. So it's some enormous integral. That's all we really need to know in some sense at this point. So you have this big family of integrals, but what one is able to prove quite easily is that in fact these are rational functions in QV to the minus S. So here are the basic facts. Sorry, this is for the exterior square. Right? So this, right now I've just written down a family of integrals, and what are the facts? Well, so the facts due to Jacques and Shalaika are that one, well, the same kind of facts, but a little more involved for each choice of W and phi, this function, phi, whatever, JSW phi, sorry, JSW phi is in fact a rational function in Q to the minus S, and moreover, the analog of this statement holds. So anyway, but so how do we do that? So first of all, the fact is, as one varies, sorry, W and phi, you get a bunch of rational functions. In fact, they give you a fractional ideal of one gets not just a vector space, but a fractional ideal. So you take the vector space generated by all of these, and that actually turns out to be a fractional ideal with respect to the ring. Which is a principal ideal ring, and therefore its generator is a single element. Okay? Take the generator, it's a priori a rational function, but thanks to the theorem of Belt, the generator has the form. So once again, let's call that a polynomial okay, 1 over a polynomial, you can take it to this form. And moreover, if V is unramified, is finite, unramified, well, no, not quite, so I have to wait. So I don't yet know that this is the L function that I started with. You know, I have the same kind of theorem here, right? So I just have something. Here they've shown that it's unramified. You get the right L function, but JS only tell you that there exists a choice W and phi such that JS W phi is the correct L function. But notice you have a so you know what I'm going to do is I'm going to define my Jacquet-Shalaika L function as this object. What I have is something in terms of W and phi. It's not clear they're the same, and it turned out to be a fairly tricky problem, right? So you have a definition of L function as some kind of generator of an ideal. On the other hand, you have a choice of local data which gives you the right thing. There's a priori no reason to just say that they're equal, but in fact they are. So anyway, so even at and this is only for the unramified places, okay? So at the ramified places you certainly didn't have that equality before. Okay, so now I will come to the more or less one. Some cannot, the usual vectors, the unramified vector and the standard function on PR. So of course we know what they are. It's not there exist. I can tell you what W and phi are, and you can compute it. But you know it's not clear it's the L function defined as GCD, right? Okay. So here's the last part of the story. So coming to the actual point. So define this thing to be the Jacquet-Shalaika L function. So as you can see, we have actually 3 objects. 2 of the objects fortunately have been proved to be the same, but that object stands. So why do we consider 2 different methods of construction? Well, first of all, it wasn't clear when people were doing it which would work and give you the right L function, but also more importantly, different L functions encode different kinds of information. So the integrals, the Rankine-Selberg integrals, often encode representation theoretic information in the form of period integrals and are closely connected to things like Shalaika models, whether representations have them or not. So you can read off different kinds of information from different kinds of L functions. From the Shahidi L functions, it's perhaps easier, and Galois L functions, it's easier to read off properties of functorial lifting, with which the analytic properties of exterior square are closely connected. Okay, so let me state a theorem, and this is, well, part of it is already there, but another one is more recent, and all of this is joint. This part is joint with Pramod Kewat, a former student who is not yet looking for a job, but anyway. So the theorem is the following: if V is finite, then so we have the exact analog of Henyar's theorem. So at all places, all finite places, we know that these two are equal. So now all 3 L functions at the finite places are known to be equal. So let me just say a little bit. So in 2012 actually we had a slightly weaker statement essentially for discrete series and whatever we could do. So a very brief word about not so much the details of the proof but about the structure. So how do you prove this? So step 1, prove this for pi v square integral. Okay. So that turns out to be the sort of technical part of the proof. It's based on previous results, a previous result of Kewat. Okay. Now step 2, you have to go from the square integrable, or actually maybe I should say quasi square integrable, okay, whatever that means. And step 2 is you have to go from quasi square integrable to all representations, all irreducible But there is a way. So step 2, prove the following formula. What's the formula? So it turns out that every irreducible generic representation of GLNFB is in fact induced. So I've written if pi is induced, but pi is always induced from quasi-square integrable data. Okay, so from quasi-square integrable, say pi 1, pi k, all right? Then you want to prove the following formula. Minutes. So I'm going to express this as a product of exterior square L functions of the square of the inducing data. Right? So that's say I equals 1 to k. So LJS pi exterior pi I exterior square, and then there's something called there's the Rankin-Selberg L functions that come in. And here it doesn't matter which Rankin-Selberg L functions I take, they're all, again there are 3 constructions, they're all known to be equal already. So I can put LJS, but nothing really. Okay, right. So on the Galois side, the analog is just pure linear algebra, there's nothing to it, okay. But on the Jacquet-Shalaika side, on the automorphic side, this turns out to be somewhat annoying to prove. So the reason I've stated it this way is, so originally we assumed this formula because it was stated in a paper of Kogdell and Piatitsky-Shapiro, but as it turns out, no proof has ever appeared, and one of the referees suggested we should really write a proof up. So anyway, I asked Kogdell, and he says that they had a very involved proof which seems to have been lost in any case. This is from 22 years ago. So in any event, so we reproved this formula now, and so it's good. So this is done. So once you have both of these two things, so this kind of formula is anyway known on the Galois side. So once you have step 1 for the quasi-square integrable and step 2, you're done. So you get it for all representations. So done for all representations. So all being, of course, irreducible generic representations. Okay. So the point is now, there's one remaining difficulty, which is that we don't know that the Jacquet-Shalaika L function satisfies this equality, the Archimedean places. Okay, but because we know that the Jacquet-Shalaika L function is the same as the Galois and Shahidi L function at all the finite places, we know that it satisfies the Dirichlet series, satisfies the correct functional equation. Okay, all right. So because of the equality, okay, LJS, this one. So just product over the V over V finite, LJS S by V exterior square satisfies FE. And of course it satisfies a finite number of poles because we know that from Shahidi, from the Langland-Shahidi business. So we know that, and of course, and FNP. So it satisfies a finite number of poles properties, and it has. So now we have all the 3 things in place. Okay, so now a very brief idea. So I'm going to get into the last part, and I'm only going to say a few words because it's kind of really messy to write down and a little technical. But here is the point. So how does one now go to the nice thing? Okay, the point is when you have an integral representation, and in fact I don't need this one, but I need some modification, so this is why I didn't really want to get into it. So how does one go from meromorphy to niceness, right? So we've got to the point where we have the 3 things that we want. So the question is how to get to the nice situation. So of course there are some normalizations involved, and they are the following, which is one, of course I'm going to start with a global unitary cuspidal automorphic representation, and I'm going to assume that the central character omega pi is trivial on this R plus factor which comes in V del. Okay, so I'm not going to say that, but modulo certain normalizations. So what's the idea? You see, when you have an integral representation for an L function, you can invert the integral representation. So roughly speaking, and I'm going to be vague here, so if I have a functional equation of this kind, so maybe I should call it sigma because I've used pi a lot. It's not the same pi, right? Okay, L1 minus S sigma. Let's assume things are self-dual. That's not going to pose a problem. Then what happens here? Well, I can invert this integral representation. That is, I can take Mellin transforms ds. So say for real S equals sigma large. Oh, I have sigma already. Okay, so real S equals u large. And so I do the same thing here, right? When you do that, say y to the minus s ds. Well, the point is, because you have an integral representation, now using the standard tools of fragment, Lindelof, etc., you can kind of shift the line of integration, etc. The upshot is you get some function of y here, some other function of y, but what you're left with is the residue. So this, what you're getting is something like this: f of y minus or plus g of y, it really doesn't matter, equals q of y. Okay, and this q of y is the sum of the residues of the poles that you have, that you encounter as you shift the line of integration. Okay, so what does it? Its structure looks something like this: c alpha y to the alpha. So maybe c alpha of y to the alpha, and say alpha is just being summed. Maybe I put j here, maybe instead of alpha j. Right. So j equals 1 through L, where L is the number of poles. What does this look like? This looks like, well, rather than writing Cjy, maybe I should write Cj of log y. I'm sorry, Cj of log y to the alpha j. Okay, and what is Cj? Cj of x is just a polynomial. Okay, and now the interesting thing is these alpha j's here can be read off from the poles, right? So in fact, alpha j is simply half minus the pole. So if beta is a pole, the alpha j is just half minus beta. All right. So all the information of the poles is accounted for in this expression. So I know this is sometimes called, I think, the Riemann-Hecke-Bochner correspondence or something. Right? Now the point is in this. So again, I have a fairly general situation, so I won't get into the details. But the point is, when you invert the representation, you see now you have an integral representation for your purposes, which means that these functions will in some way involve integrals over w, some w prime, and they will have something like y to the s. The point is, you can write them like that, roughly speaking. Okay, I'm certainly not being precise here. Now, because the integrals have this structure and they remember the representation in terms of the vector w, what you can do is use the action of Hecke operators. And if I took an unramified vector at some place and stuck in a Hecke operator here, of course, it just multiplies it by a constant, namely the eigenvalue of the Hecke operator. So if I replace Tp on the one hand by Tpw, right, so whatever it is, this will mostly be w again. If I replace that, on the one hand, nothing much changes. All that will happen is I'll get a lambda p here, maybe a mu p there, but the poles are going to pretty much remain the same. That's not going to change anything, right? I'm essentially getting the same L function. So their exponents occurring here are going to be the same. All right. But now with the Hecke operators, I can actually figure out, so the real point is these things capture the asymptotics of these functions as they go to 0 or infinity, depending on alpha j being positive or negative. And the point is, I can actually write out the Hecke operator using the Ka-K decomposition, and I get the double coset as a sum of single cosets, and I get an action on W, and then I can actually figure out what happens to the asymptotic.